my name is Mathias Gottschlag, and in this video I'm going to show how automatic core specialization can mitigate the negative side effects of AVX 512 instructions. AVX 512 is a SIMD instruction set extension which provides both flexible vector operations as well as very wide 512-bit vector registers, both of which allow AVX 512 to exploit a bit more data parallelism than previous instruction set extensions. In encryption, for example, AVX 512 was shown to provide substantial speedup for the poly 1305 MAC algorithm, which subsequently led to an inclusion of a very similar implementation in the popular OpenSSL library as well. However, shortly after, in 2017, it was shown that this very implementation could, in some scenarios, actually slow the whole web server down by 10%. Also, Intel advertised AVX 512 as being able to speed up some machine learning workloads by a factor of more than 2. However, last year it was shown that applications running in parallel to those machine learning workloads were, again, slowed down by 10%. So in this video I am going to describe a technique which is able to prevent this slowdown and which does so without requiring any manual modifications to any of the applications involved. However, first let me explain the problem. The reason for these effects is that AVX 512 instructions operate on those large 512-bit vector registers and therefore consume lots of energy per instruction, whereas in a heterogeneous workload, other parts of the workload may only operate on regular 64-bit registers and therefore consume a lot less energy per instruction, which means that those workloads have a high degree of power variability. And that's a problem because the performance of modern CPUs is mainly limited by their power consumption, both due to limited heat dissipation and due to power supply limits. So in such a workload, the different parts of the workload can actually be executed at different maximum frequencies without violating those limits, simply based on the instructions executed. Now, this shows in recent Intel CPUs, as those CPUs have to slow down AVX 512 code quite a bit in order not to violate any power limits. Now, such slowdown would not be particularly problematic if only the AVX 512 code was affected. However, there are two scenarios in which other, potentially completely unrelated non-AVX 512 code is affected. The first one is shown on the left side, where the figure shows a system which first executes some AVX 512 code and then executes non-AVX code. Now, the latter can of course be executed at a much higher frequency. However, at the end of this AVX 512 code section, the CPU does not immediately increase its frequency again. Instead, it waits for some time, basically in order to implement some frequency change rate limiting. But that of course means that the following non-AVX code is slowed down. Also, as shown on the right side, on systems with hyperthreading, the two hyperthreads share one physical CPU core, so they also share one CPU frequency. But that means that if one of the hyperthreads executes AVX 512 instructions, whereas the other one does not, this non-AVX code again is slowed down. So in both these scenarios, we may have a local speedup due to AVX 512 within those AVX 512 code regions. However, overall, AVX 512 may actually cause a global slowdown due to this overhead. Now, whether we get a speedup or a slowdown is often hard to predict, in particular because the ratio between the time spent in AVX 512 code and non-AVX code can often change at runtime. So ideally, we would have a solution which could prevent this kind of overhead at runtime when it actually occurs. Now, our idea here is to employ core specialization to separate AVX 512 code and other code. So we take a subset of the CPU cores, which we call non-AVX cores, and those cores must never execute any AVX 512 code. Now, as a result, those cores will always execute at higher frequencies, whereas the other cores, which we call AVX 512 cores, may execute AVX 512 and may therefore be slowed down. However, only those cores are slowed down, so overall the frequency impact of AVX 512 is substantially reduced. Now, for this kind of core specialization, we need to have some kind of categorization of tasks. We need to know when tasks are going to execute AVX 512 instructions in order to migrate them to the appropriate types of cores. Now, initially we assume that all tasks are going to be non-AVX tasks. So we think that tasks are probably not going to execute AVX 512 instructions right away. So those tasks initially can be executed on non-AVX cores. Now, as I said, non-AVX cores must never execute any AVX 512 instruction. So what we do is we configure these cores in a way that they assume that the operating system does not support AVX 512 at all, because that means that any AVX 512 instruction triggers an exception. Now, in the resulting exception handler, we just take the current task and mark it as an AVX 512 task instead, and then migrate it to an AVX 512 core if necessary. Now, we would also like to have a similar notification mechanism to detect the end of an AVX 512 code region. However, the CPU does not support such a notification mechanism, so what we do instead is we just assume that AVX 512 is mainly used in particularly computationally heavy parts of the workload, and those parts usually do not contain any system calls. So during each system call, we just reset the type of the task back to non-AVX task to allow it to execute on non-AVX cores again. Now, as I said, non-AVX cores must not execute AVX 512 tasks. Sometimes, however, AVX 512 cores may execute non-AVX tasks, but only if they would otherwise be idle. So mainly in order to improve CPU utilization. So basically we implement static prioritization of AVX 512 tasks on those cores. So this is just a course description of our approach. So if you're interested in the details, we invite you to read the paper. Now, we implemented this approach as a modification of a Linux scheduler, and we evaluated it with a range of workloads. The first one, shown on the left side of the figure, is basically the web server and OpenSSL example given in the beginning of this video, whereas the other workloads are benchmarked from the Parsec benchmark suite, executed in parallel with the X265 video encoder, which supports AVX 512. Now, the blue bars are the CPU time required when AVX 512 is completely disabled, whereas the green bars show the CPU time when AVX 512 is enabled again. So basically the difference is the AVX 512 overhead, which in this case is on average 11.3%. Now, the brown bars are the CPU time required with our prototype. And in this case, the overhead is only 3.4%. Now, in our paper, we show further experiments which show that this performance improvement is mainly caused by the improved CPU frequencies in our prototype. So these results show that our prototype works. However, it still has a number of limitations. First of all, the way we generate exceptions for AVX 512 instructions is just to disable all access to 512-bit registers. However, not all 512-bit operations are equally energy intensive, and only multiplications and floating point instructions are particularly problematic for performance. So ideally, we would like to single out those instructions. However, that's not possible with current CPUs, so we would like to see a better hardware-software interface there. Well, and then there are two major, let's say, implementation limitations. The first one is that, of course, our prototype generates additional task migration between different types of cores. Now, on NUMA systems, migration between different NUMA domains is particularly costly, and our prototype is not yet NUMA aware. So in the future, our prototype should try to minimize the amount of migrations between different NUMA domains. Well, and then finally, currently in our prototype, the number of AVX 512 cores still has to be manually set by the user. And as part of future work, we want to extend our prototype to automatically determine the ideal number of cores simply based on the CPU load of the different types of cores. So to summarize, AVX 512 instructions can substantially slow down other potentially completely unrelated code. Now, we propose a technique to separate AVX 512 code from other code via core specialization, and our evaluation shows that such an approach can substantially improve performance. With this, I'd like to conclude my talk. Thank you for your attention, and if you have any questions, feel free to ask them during the Q&A session.
So from errors, it's well known that applications and workloads work more efficiently when they match the underlying system. The underlying system's native unit size, like 4 kilobytes for memory pages and 512 bytes for disk sectors and the like. Is the power use of AVX512 instructions 8 times that of a 64-bit instruction? If so, would the problem go away if everyone designed their applications to operate on a 512-bit aligned data units? So if you match your ISA to sort of match exactly this, these hardware ISAs and the AVX instructions, would that sort of take care of the memory problem?
So, I mean, it's not that bad. After all, the AVX 512 or the floating point unit there only occupies a small part of the chip. So I don't know how much the power difference is, but it's not that bad. And the other problem is that, well, these white vectors, I mean, they can't really be used for that many problems. I mean, many problems just don't provide as much data parallelism.
So Daniel Littai asks, doesn't AVX 512 on a single core doesn't it affect the entire socket power profile? So can one core affect everything?
That used to be the case, I think, well, with Intel Haswell, the Intel Haswell architecture. But at least I don't know I don't know about Broadwell, but at least starting from Skylake. So when AVX 512 was introduced, each single core can actually apply different power profiles. So some can operate on AVX 512 frequencies, whereas others operate on non-AVX frequencies. But that's just been introduced with Skylake.
And when there's a large number of cores, that many of them are going to be dark because of the core just can't support the chip can't support all the cores. Would your stuff still be applicable to there? Maybe I don't have 2 threads. I just spread single threads on different cores, or I have a lot more choices.
Yeah. I don't know whether I understood the question correctly, but in a single core scenario where all the power headroom is concentrated on one physical core, these frequency differences are a lot lower because a single core can't. This is mostly a power supply limitation, and a single core apparently can't really reach that power supply limit. So on a single core or a single thread workload, the frequency difference is just 100 or 200 megahertz compared to almost a gigahertz for a all-core scenario.